So in this video we will be discussing full associative cache. In fully associative cache you have to understand that the n value is b here. That is, there is only one set. You have to understand one important thing here is that the number of set here is 1. How the number of set becomes 1? You can understand if our sets formula is there, it is what? B by n. It is 1 when the number of n is here what? N's value is the number of blocks. So b by b value would become what? 1, right? So the number of set becomes 1 in that way. The number of ways in the set, there is only single set, and in the single set there are number of blocks ways, that is b ways it is there. A single set has b way. That means if you see here in this image, this is my single set. Let's say I have 8 blocks in it. So that means a single set, this is my single set, can have 8 ways: way0, way1, way2, way3, way4, way5, way6, way7. And in anywhere in this single set 0, let's say this is set 0, I can put my address. My address can be in any of this set. So that is what it is written. A fully associative cache is a logical extreme of the set associativity. The recall from before, a set associative cache has S set and each set has n ways. So in fully associative there is only one set and the number of ways is the b, that is total number of blocks. So there is only one set and every single block in the cache is a way in that particular set. In that set every block is there. So here that image I showed you has 8 ways, way 0 to way 7, all belonging to a single row, each having a valid bit, tag bit and data bit. Understood? That what I have shown in that image. Now a memory address came. Whenever a memory address comes, this memory address, what happens is that this memory address can map to any of the block. In direct mapped cache an address is coming and that address can map to exactly one slot only in direct mapped cache, so collision occurs. And in set associative, an address map to one set, but it can sit in any of the n ways in that n set associative. But in fully associative cache, an address can go in any block in the entire cache. There is no set index in there. There is only one set, so there is no set index. So the address can be split just in tag and byte offset. This is a maximum, that is in our address is split. There is no set index. There is no set index. If you consider there is no set index and our address is divided on tag and byte offset only. There is no set index here. Byte offset and tag is only there. There is no set index. Why there is no set index? Because there is only one set in which it can go, so we don't need to specify the set index here. So therefore you have to understand that a memory address scheme, it can go to any block in that particular set. It's such a b way, like you can say in n way set associative, fully associative is like a b way set associative, right? So in direct map the number of sets is the number of blocks and the number of ways is one way is only possible for each of the block. N way set associative means the number of set is b by n, the number of ways is n ways. In fully associative the number of set is 1 and the number of ways is b. B ways you can basically put the memory address. Now there is an 8:1 multiplexer, like here in our two-way set associative diagram you can see this multiplexer. In the early video I just said comparator, I hope. I think it's an error, it's actually a multiplexer. Okay, I don't know why I have said. This multiplexer would decide the data, right? And here what, in 8:1, after 8 comparators at most 1 will signal a hit. So a multiplexer uses that hit signal to select the correct data block output among these 8 ways and forward it to the processor. So this a multiplexer, there is one hit from here. Now the comparators, these are the comparators. Now there would be a lot of comparators because 8 comparators would be needed, right? Since for 2 ways we use 2 comparators. So if there are 8 ways, then 8 comparators is there, and any of them would give us the hit, and that hit, from where that hit is there, that will decide which, in this multiplexer, which data you have to use. So we will use an 8:1 multiplexer to decide. If there are 64 block, let us say in here only 8 blocks were there, so we use 8:1 multiplexer. If there are 64 blocks, let us say, then we have to use 64:1 multiplexers, right? And similarly here there were, for 2 ways there is 2 comparators, then here if there is 8 ways, then there would be what, 8 comparators also in this diagram. That is why we are not drawing this diagram, because it will be very complicated and a large diagram, right? And the multiplexer would be 8:1 to decide the data. That is the thing that you have to understand. Now the conflict misses would be fewer here, because any block in the memory can go to any cache source, so there would be no conflict, there would be never any conflict misses happen. If here no two address would fight for the same position. The only misses are compulsory, compulsory misses would happen, and capacity miss would happen. This makes fully associated theoretically optimal in terms of miss rate. For miss rate, it would be optimal. Compulsory misses are that misses which is happening during the first access. During first accessing, there would be, cache would be empty, right? So at that time, compulsory misses would happen. That means during the first access, there is nothing in the cache, so those misses would happen. And also here, conflict misses not happening here, because in any set, that is in one set is only there, so conflict miss is not happening. But if the cache capacity is full, then capacity miss would happen. So you have to understand here that in here what is happening. You can have, there is chance of having what, capacity miss is happening. Similarly, the compulsory miss would also happen. Only conflict miss is not happening, but capacity miss and compulsory miss would happen. I hope you understood what do we mean by capacity miss and compulsory miss. Compulsory miss is the first accessing miss, and capacity miss is that if when the cache becomes cache size finished, cache capacity finished, then capacity miss would come, right? But conflict miss is not there in our fully associative cache. That is this sentence we have covered. Now, best suited to small caches. This is best suitable for small caches. See, the hardware cost is the limiting factor. Every block you add requires one more comparator. So what happened, and a wider mux. So hardware is very much difficult. If you have like for 8 and 64 such words cache, it is fine. Small cache, this is okay. Like you can bring 8:1 multiplexer, 64:1 multiplexer, and 8 comparator, it is fine. But if you have lot of entries, like large cache like 256 and kilobytes and all, what happen is that 4096 block is required, so that much comparators is needed, which is impractical for us. So such possibility is not going to happen. So it is only better, fully associative is better, hardware is better only for small caches, and for larger cache and all, it is not actually a good idea. Now let's understand what do we mean by this term miss penalty. This is the time required to load a missing block from the next level of the memory into the cache. This applies to all cache, not just fully associative cache. It is the latency cost paid when a lookup result in a miss. Minimizing miss penalty is the central goal of the cache design. Miss penalty means the time required to load a missing block from the next level of the memory, that is from the DRAM or lower level cache, into the cache. That means we have to understand miss penalty means what, the time required for taking that data from the maybe it can be from the main memory. Let us say by now from main memory, let us consider. So from main memory we have to take the data. So the time taken for the, if miss occurs, then you have to take that data from the main memory and put it into the cache. That time is called as miss penalty. And the good cache design means what, this miss penalty time is less. The time taken to load that data from the main memory to this block to add it into that missing block, that time would be less in an appropriate ideal design for the cache design. Okay, minimizing this miss penalty is one of the goal. So what do we mean by miss penalty? Miss penalty is a time required for us to load a missing block from the next level of memory. Means it can be, if you have multiple level cache, then you have to go to the lower level. That multiple level cache thing we will discuss later. Right now you understand that the miss penalty means the time that is taken to load this missing data from missing block from the main memory and putting it into cache. That time is the miss penalty, and ideally we have to think about minimizing this miss penalty. That is the central goal for designing a cache. So this much we have to understand about fully associative. Thank you.